Assalamu alaikum and welcome to the Learning Mentor. In this video we are going to be covering how to do ANSYS Fluent CFD simulation of an airfoil, and we are going to learn some CFD basics. This is a basic tutorial. Don't make it an obvious that these will help you in your research purposes. This will help you gain basic knowledge of CFD. So I'm already making it disclaimer that I am not a professional. I am going to teach you how to do CFD as an introductory, as a beginner. So first of all, what we need for our simulation is a geometry or a profile that we should be simulating. For our case, we are going to be using NACA 23012 airfoil. In my previous videos, I have created an airfoil in SolidWorks. We are going to use that similar file, and I am also providing that file in the description of this video in IGES format that you can easily download and open it and practice for yourself. If you have any trouble creating that file or any airfoil, you can comment down below and I will surely help you in that. So let's get started. Let's first open our ANSYS Workbench. Now, to be honest, you have to first save your file so that your file doesn't corrupt. So first of all, I am going to save it, my file. I am going to save it on my desktop named as CFD tutorial 1, CFD tutorial 1. That has been saved. Now I am going to import an ANSYS Fluent project to my project schematic. You can also do like this, that you can first import a design assessment and then link it to multiple files, but I don't prefer that, so I am going to create in my own way. So first of all, we have to import our geometry. I am going to import my geometry from the desktop. I have saved over there, IGES. You can also download it from the description. So the geometry has been added. Now we are going to open this geometry in our design modeler. We can also edit in space claim, but design modeler is some efficient to use, and almost you can find every video on YouTube that has been using design modeler. Very few people use space claim as a modeler. Now we are going to generate by using this electrifying looking like button and clicking on generate, and this airfoil, this beautiful airfoil has been generated. Now we have to do a beautiful simulation of this beautiful airfoil. For that, first of all, we have to create an fluid domain. So for fluid domain, I am going to select XY plane from here and look at, do that because it's easier to draw in 2D. Now as you can see that my screen, the airfoil has been gone. Why? Because the units are by default set to meters. If I convert it into millimeters, then my airfoil will be visible. If you have drawn your image or your airfoil in inches, you would prefer to simulate, change your units to inches, then you can easily simulate it. So as I have created my airfoil in millimeters, so I am going to convert my units into millimeters. Now I am not going to zoom it like by cursor like this and weight it. So simply the trick is to F7 it or use this particular button. You will get it to your window. Now this particular airfoil, we need to create a fluid domain. Now what's that fluid domain? Fluid domain is where our fluid or our air will be flowing. Now there are two regions in our fluid domain. One is the upstream region and the second is the downstream region. Now an airfoil creates a wake region or a wake profile in our downstream region, and that's important to be studied. So we are going to take some measures that will help us study the wake region or the downstream region more for the airfoil. So I am going to first create a simple rectangular domain. We can also use a C-type domain or an O-type domain for our simulation, but as we are dealing with basics right now, we are going to create a rectangular domain. So XY plane, go to sketching from here and select rectangle and enclose this airfoil into a rectangular. Now as you can see, this is enclosed by this rectangular box. Now we are going to go and dimension, because without dimensions we cannot do anything. Dimensions in our fluid domain is a very important thing. We must consider dimensions first. From dimensions over here, if I want to go to back to draw, you might be like, where is my draw button? Where is modify? So you click over draw, you get draw. You go to dimension, you get dimension. So from here I go to length and distance. First I select these two horizontal. These are vertical lines, but I am going to mention it as an horizontal distance. Now this horizontal distance has been measured. We can also do from here the horizontal distance and vertical distance separately. For horizontal we should select horizontal, and for vertical we should select vertical, but in this, and to simplify it, we are going to select length and distance. So now for the vertical dimension between the horizontal lines, I am creating the dimension. It has been created. Now what are the dimensions? How we select the dimensions? So as we know that our span or our chord length is 100 millimeters, so we are just going to double it by our hand rule. So I am going to just double it for the upstream region, and I am going to triple it for the downstream region. And for our vertical heights, I am going to make it equal to our chord length. So you can see that our airfoil has been enclosed in an study region. Now this rabbit will be tested. Now since it is 2D but our airfoil is 3D, we need to make it 3D. So for making a rectangular into 3D, we use extrude. So by selecting extrude, now you can see that it is extruding in only one direction, and in the object I have created, the origin is centered. Now making an object centered has its own perks and cons. So I have centered it. You can create it non-centered, it's up to you. Now I am going to apply to this sketch. I am going to add material as frozen. Direction will be both directions. It is starting for the middle, and it will be symmetric. Both directions are the same, and 50 millimeters each side. You may be thinking why I am selecting 50 millimeters. So basically we are doing an airfoil simulation. If we were doing a wing simulation, we may have increased it to 60 or 70. In an airfoil simulation, it is necessary that we make our fluid domain equal to the span of our airfoil. That will make our simulation perfect, and it also makes our simulation 2D. It's maybe 3D, but we are making it 2D by enclosing it in a 2D box. We can, in another video we will do a simulation of wing, and we will tell you the difference, what is the difference between wing and what is different between an airfoil. Now I am going to generate it. Now this is completely enclosed in it. Now as you can see that this airfoil may be symmetric airfoil. So now for this airfoil we need an angle of attack, and for this case I am choosing an angle of attack of 10 degrees. So to create an angle of attack of 10 degrees we are going to rotate it around its origin. So to rotate this airfoil we are going to go to create and go to body transformation and rotate. Now as the rotate command says to select a body. Now what is our body? Our body is our airfoil. So I am going to select my airfoil. Now what is the axis direction in which it has to rotate? So we can see from our origin that we have to move it in the Z direction. Which plane does represent perfectly? So it is the XY plane which represents our direction perfectly. Okay, so now for the angle it's 10 degrees. You can see that over here we are moving it a 10 degrees shift, and generate this file so that it rotates. Okay, now our airfoil has been perfectly rotated. It has been given an angle of attack which will produce a lift force, which we will be measuring in our result section. Now I am going to create a boolean. Now what's boolean? You may read it in CFD books. We are going to subtract it. We are going to select the target body, which is our fluid domain, and our tool body. Now you may think why I am telling you to go study. I also don't know. I actually do know, but not everything on YouTube is free. Select this tool body. Maybe I should tell you, we are subtracting it because when we are creating a fluid body we are flowing it through, but we are subtracting in a portion in which it will not flow and will give an impression of a much part. There is a part over here there which will act as an part, but actually it's empty. So that's what the boolean command is. You can further read it on internet. Tool body, select this body, apply and generate. So as you can see, as I said, it will subtract it. So it has subtracted it. See, it has been subtracted. Now as it has been subtracted, it has been made a fluid domain. What should we do next? We should go and mesh it, as the workbench says, go and mesh it. But no, because we are intelligent people, we will first create an body of influence over here so that we could study this downstream region well. Now going to sketching, selecting this outsider plane. It's not working, so I am going to select XY plane, sketch, rectangle, create a rectangle to study your downstream region that cuts the tail of your airfoil, this tail of your airfoil, and ends at your downstream region. So extrude it. I'm not giving it any dimensions. I'm saying that it will be multi-direction and it should have some material. Generate. Here you can see error. It shows some error, that there is some error in it. Now what error might be? Because we have created two bodies of extrude. Now it is confused between what should it consider as body. So to fool ANSYS that we have created such a body, we are going to suppress it. As we have suppressed it and generated again, now we are safe. We can easily do our simulation further. Now let's check whether our mesh solver opens or not. So opening mesh, just double click it, your mesh will open. Mesh design modeler. Here you can see the bus bell that is showing that our meshing system is being launched. As you will have a good computer, it will run much faster than mine. This is not, this is mesh, this is design modeler, this is mesh, M for mesh, DM for design modeler. Now you can see this body is over here. I am going to suppress this body because it is quite irritating for me right now, that I am going to label it. For the first operations, it is quite irritating for me. So I am going to suppress it. It has been suppressed. Now first steps first, we are going to name it, that what are our inlet sections and what are our outlet sections. So to name it, what we do, we first select it. Make sure that from the above your face is selected and single select mode is selected. Now what we will do, right click it and go to named selection, create a name selection, and what should be its name? Inlet. Okay, so I have named it. So here shows inlet in our name selections. Now we are going to name it this side outlet. Okay, we have named inlet and outlet. Now we should also name this airfoil as well. Now if I select it like this, only face is selecting. To select this airfoil, we are going to move to select mode and then box selected, and use our box to select this airfoil, and we are going to name it as airfoil. Okay, so we have named it. Now we are going to create mesh. Now to create mesh, first we should think that which things are important for us. Is this region important for us for our mesh? No, this fluid will be stabilized. Now this region and our backstream region is important for us. So to save computational power, we will emphasize the mesh over here and make mesh over here clean, and we can just mesh normally in the outflow regions. To do a quick simulation, I am going to right click over here in the mesh, insert sizing. Now in this particular mode of sizing, you can either select this whole body if you have this body selected, and you can select this body and go to geometry, select this body. Why it is not selecting? Because our single select is open. Go to and change it to single select. Boss select was selected, change it to single select. Now we can select either this whole body and make a sizing operation, or we can do some intelligent work as we are intelligent people and go to options and select edge from here. Select this edge and apply. Now we are applying our mesh to this particular edge. Now from this type there are multiple types of meshing types given, but we are going to select number of divisions and we are going to apply 200 divisions to it, maybe 400, and depending upon your computational power of your computer. Now I have selected this edge. I am going to apply the same to over this. So adding, inserting, sizing, edge and be selected, this side selected, same 400 for this number of divisions. Now we are going to select this internal face by going to insert, sizing, and select this internal face of the airfoil. As you can see, the whole face has been selected. Apply. Now as the face is selected, we have added face sizing. As we are selecting edges, we are adding edge sizing. Now here we are going to use element size, and we are going to define element size as 5 mm or 4 mm depending upon your computational power. So for in this case I am going to select 4 mm. Okay, I have selected for the inside 4 mm. Now we are going to create an inflation. What is inflation? I will leave a link down below. You can study about it much more. Now what will be our geometry in which we are going to apply inflation? We will select this whole geometry because we are applying in this geometry inflation. Apply, and what will be the boundaries that will be applying inflation on? We are going to select this airfoil. Make sure you only select this airfoil, otherwise the mesh will be deteriorating. Apply. Now these are some terms which I am going to be setting. You may study it further to gain a grasp over your CFD simulations. I am going to select total thickness, and I am going to select maximum thickness as 2 millimeters. I am going to select it as 6 millimeters now. Okay, so 6 millimeters, as our edge size, face sizing was 4 millimeters, so we need something bigger than that so that our mesh is not destroyed properly. Now we have created inflation, we have created face sizings of both. Let's generate the mesh, but before that first select the element size to be 10, the default element size. Now what does default element size do? It defines what the other parts will be, what will be the element size of the other parts of the mesh. So that has been defined over here. So inflation has been added, face sizing has been added, edge sizing has been added, and we have also set this. Now remember, we added something in the start which was an body of influence. Now we have to uncover it, and we are going to go right click in this workspace and select unsuppress all bodies. This body has been uncovered. Now we are going to insert and sizing. We are going to select this whole body and apply. We are going to select body of influence and selecting this particular body for the influence region. Body sizing, selecting this. Now see, I am having trouble in selecting, so I will go to box select and select this. So this body of influence has been selected. Apply, and we will make it similar to what we have made over here in this airfoil, which is equal to 4 mm. We are going to select 4 mm for here as well. I am going to make it 5 or 6 mm so that my computer doesn't hurt, because I love my computer. So this has been added. Now generating mesh, it may take time, because mesh always takes time, and simulation means taking your time out of your life. Now you can see that our mesh has been completed, and an error has come. Inflation created stair step mesh at some locations. We could ignore it as well. You can see that our mesh has been created. The mesh typically around this region is not so dense, but as you zoom in, this particular region has smaller element sizes. And if I zoom in more to our airfoil has this type of mesh. Now what's important in doing CFD is that we should know that what is mesh quality. Now as I see over here that we have gotten a good amount of mesh over here. Now I am going to check my quality of the mesh. If my mesh quality will be alright, I will be proceeding it. If it's not, I am going to recheck my mesh, change some element sizes, and then further proceed. Now from mesh metric, I am going to select orthogonal quality. Now as we see that my average mesh quality is 0.76 and minimum is 0.10511. Now this is a decent mesh quality. Typically we need to be, minimum should be greater than 0.1, 0.01 in the orthogonal quality. We are alright in our case, but we can further improve our mesh. If we just decrease this layer, it will improve. Or we can add mesh region over here. As you can see, this point is not much not correctly meshed. It has many points converging over here. We can define mesh over here. So depending upon your computational power of your computer, you should improve your mesh so the results will be more accurate. But for now we are going to proceed because already the video has been too long for you. You must be bored. So back to our ANSYS workbench. Update it first. Update your mesh first of all. Remember, update only the mesh, not anything else. This is a beginner's tutorial, not for experts. Experts, refer to another video. Now we are going to set up and edit this. Now here shows Fluent launcher. I am selecting double precision parallel. I have 8 processing cores, so I am going to select it. I am selecting 8 processing cores from my here. You can select serial if you don't know what are your processing cores. I am just going to select parallel so that the performance of my is better. Now as we have loaded it, we have loaded our model mesh into the Fluent post processor. Now first of all we will check that whether our mesh is correct or not according to our Fluent. It has checked and it has said done and says no error, which means our mesh is alright. If it gives you an error, check mesh again, because as it doesn't give us any error, we are going to say okay. Now we are going to say report quality. Now it gives some errors in the mesh quality. Minimum orthogonal quality as -1 on cell zone 3. We should reduce this error, and it is giving some answer to it. We are ignoring this error right now to complete our tutorial. We are going to do a steady state simulation, which will be pressure based, not density based, and the velocity formulation will be absolute. Now selecting this energy model will just increase the computational time. So we are going to go in viscous laminar and select K omega SST model. Go to K omega and select K omega SST model. Let this be same, and we are not selecting this, we are not selecting this. If you have good computational power, you should be selecting this, and I am going to select OK. CFD is all about computational power. Now going to methods directly. No, we should not go to methods. If you do that, you are a fool. Go to boundary conditions and set the inlet velocity. Now we are going to select this as 48 meter per seconds. We are going to select an high velocity which will be equal to 30 miles. This is equal to 30 miles. We are selecting 48 meters per second, which is equal to approximately equal to 30 miles, and I am going to select OK. The inlet conditions are the most important thing in an CFD simulation. Then we are going to go in methods. We are going to select coupled, and we are going to change all of our first models to second order upwind models, and pseudo transient. We will going to select pseudo transient, and we are going to make some reports as well. So report definitions, go to report definitions, new report, force report, lift report, and lift force shall be obtained at airfoil. Look how it is important to name the regions airfoil, and force vector will be y. Okay, so report files, report file to create, report plot as well, and okay, I am going to also create a lift coefficient. We have created a drag over here, we have created a lift over here, so we have to create a drag over here. Force report drag, and on the airfoil report file, report plot, and okay, close it. And for initialize it, I am going to hybrid initialize it. You can also standard initialize it by going inlet and then initializing it. Both methods are the same almost. We have initialized it. Now it has been initialized. Now I am going to go and do some run calculation activities. It will take time. Now since our simulation has been taking too long, you can complete your simulation till it converges, but we are going to end it right now by clicking on the stop button when this 200 iterations finish. So it currently is at 195. We are going to complete it at 200, and then we will further proceed to the verification step, that whether our simulation is partially correct or not, because since we have not reached the convergence point right now, it doesn't mean that our answers will be correct. It might be near to correct, but it will have some error. We have to find that error and we have to minimize that error by using a suitable mesh that would converge it very soon, rather than taking that much time. It may take hours, it may take days in a simulation. Now since 200 has been reached, I am going to stop this. You can continue this at its converges. I am going to stop it right now, and we are going to now see our plot. Now first, to see our plot or our graphics, we are going to see that whether our contour, we are going to go in results, and then we are going to go contour, and from contour we are going to display our airfoil, that what forces are being applied on our airfoil. Save and display. It's represent our forces. Now as this is contour file, you can see that our leading edge is a little bit disturbed, which means that we should have some good meshing at our leading edge so that the mesh is not much disturbed. So I'm going to draw the mesh as well, display the mesh as well of the airfoil. Okay, close, save display, So you can see that we should refine its mesh in the airfoil to get some good results. I have some results which I will paste in the end of our video which are completed. Now this is the result, but you don't know the values. This is only the contour of the airfoil. We now need an plane as well to show the contour of the plane. So for a plane we are going to create a plane. I preferably use point and normal and go to the origin by making the point 0 0 0, and since this is the y direction, x direction is here, I am going to select 0 I y 1 and create a plane and close, select plane 5, save display. You can see this is what is cutting. Another plane has to be created. This time it will be in the x direction and another in y direction, z direction. So I have created 3 planes. I am going to display it all. So the z plane was the correct choice. As you can see that there is some red portion over here which represents that this is the this is our lift force being created over here. Pressure has been created over here. Now, and there is some wake region created over here. We can see the velocity profile by going to vectors and creating a vector plot with a scale of 100, which represents the flow over the airfoil and plane 7. So you can see the velocity profile of the air around the airfoil. You can change the scale factor to clear it. Make sure you select planes as well and airfoil as well. Increase the scale to something like 50. Save and display. You can see the velocity profile of the airfoil. You can see there is a vortex created over here in the wake region. This is our CFD simulation. Now we have to verify our results. So we go to reports. I am going to create a report of forces over airfoil in x direction, which is the drag force, and the drag force comes out to be 2.3301. I am going to paste it on a notepad. So the drag force is 2.330123. Now the lift force, for the lift force we are going to create, which is in the y direction, print, which is equal to 8. Now we will divide 8 by 2, means this value by this value, which will give us lift to drag ratio. This value divided by divided by this value gives us a value of 3.627, which for the NACA 23012 airfoil is not accurate actually. The major reason behind it is that we don't have enough iterations, we don't have done enough iterations. So that's all. You can further improve your CFD simulation to get better results. How we will be doing a next part of it to make it good. So Allah Hafiz for now.